Hello class, today we'll be doing the first video of the Frank-Hertz experiment. We'll cover a little bit of theory before we move on to the next video which will discuss the apparatus itself and how the experiment works. Okay, so the Frank-Hertz experiment, it was named after James Frank and Gustav Hertz. And what it did, it proved the existence of excited states in mercury atoms. In doing so, they helped validate, support the Bohr model, for which and then that managed to get them, they earned the Nobel Prize in 1925. So before proceeding to the theory behind the Frank-Hertz experiment, let us talk a little bit about what is actually the Bohr model. So take this picture for example. So the Bohr model stated three simple things. I'm just oversimplifying it here. But the Bohr model picture was the following. It assumes the existence of a very compact and dense nucleus that is positively charged and that has electrons orbiting around it. But these electron orbits cannot just be anywhere. They are at certain distances. So you call these orbits to be stable. Electrons like to be in those orbits. And how do you find these orbits? The orbits, to be stable, they need to satisfy the condition that the angular momentum of the electron is equal to an integral of the reduced Planck's constant, which is here. And if you don't know what the reduced Planck's constant is, it's simply the Planck's constant divided by 2 pi. Okay? So that is the equation. So this statement number 2 tells you at which distances you can find the stable orbits. Now, the statement number 3 says an electron can jump from any allowed energy state to another by emitting or absorbing radiation. So if an electron is in state with energy 1, absorbs a photon and jumps to state number 2, it's now increased the energy of the atom. It doesn't like to be there. Electrons like to be in the lower energy state. And so we'll just stay there for a little bit, then we'll fall onto its original energy state, and we'll do so by emitting the photon that is with a frequency that is mandated by the energy difference between the two states. Okay, so this is more or less what the Bohr model was. So how did they, how does this come into play when you talk about the Frank-Hertz experiment? Let me erase this. So what the Frank-Hertz experiment constituted of was this low pressure gas tube. So for a Frank-Hertz experiment, it contained mercury. Inside this gas tube, you have the following components. Okay, so what's happening here? And then here is the retarding voltage. And this will be the accelerator. Okay, so you have low pressure gas here, and then you have this filament. This filament is then heating this cathode, and in doing so, it's emitting, it's doing what it's causing is having these electrons being emitted from the cathode plate, which is held at a negative potential. So let's say cathode. And then this is your B anode. Now there's a potential difference applied, so this is negative, and then this is positive. So once the electrons from the cathode are emitted, they're being accelerated. So you can have here is where the gas is. Okay? So you have an electric field actually goes this way, and if you recall, the electric field, the electrons would like to go to the positive side. Okay, so they're accelerated, they pass through these anodes, and if they have enough energy after they're accelerated, they will be arrive at this collector plate where they produce a current, and that's read off as a retarding voltage with this. So it produces a current with this ammeter, and it's read out as a retarding voltage. So depending on the accelerating voltage, these electrons can either make it or not to the collector plate. So what does it look like if we plotted the accelerating voltage versus the retarding voltage? So this is our accelerating voltage. This is our retarding voltage. So initially you will see, so if we were to plot it, you're going to see this kind of graph. Okay, so what's happening here? So we all remember from the usual Ohm's law where we plotted current versus voltage. We got a straight line, right? But that's not the case. You could see sort of an increasing line here, although here I'm plotting retarding voltage, but if I plot it against the current, I will get the exact same thing. So this could be voltage or current. But what's happening here is, recall that I mentioned the Bohr model said that we have quantized energy states. And so what's happening is we're getting the electrons being accelerated. They're going to meet mercury atoms, and as soon as, so they're going to meet mercury atoms, they're not meeting the energy requirements for the excited states, the energy states of the mercury atom. So they continue to increase the current up until this point where you see that now we see a dropping current. So what's happened there, before they get to this, the electrons collide elastically with the mercury atoms, and then they make their way towards the collector plate, and you get a current. But once they arrive, they make it so that now they have enough energy to reach that the particular energy state of mercury, now the correlation becomes inelastic, and the electrons that were initially accelerated give up their energy to excite that mercury atom. But since they're inside the chamber, now they basically get reaccelerated, so you can consider this one mercury atom excited. And then here, if they get reaccelerated, this could be two mercury atoms accelerated. So notice that this particular peaks happen at only particular positions, and they're equally spaced from one another. So this helps prove the existence of energy of excited states that are quantized by the Bohr model. Now in the next video we'll talk about a little bit about the equipment.